Hi guys. So in the previous lecture we talked about the reflection principle, and using the reflection principle we saw that the joint density function of a Brownian motion given by Wt and its maximum given by m of t is given by this formula right here, right? This was the joint density of Brownian motion and its maximum. Now today what we would like to do is we would like to basically consider Brownian motion with a drift. Okay, and we want to look at Brownian motion with a drift and its maximum and figure out what is the joint density of Brownian motion and its maximum. Okay, but here the Brownian motion is going to have a drift. So now let's see how we're going to compute that. Okay, so let's first construct a Brownian motion with a drift. So let's start by considering a probability space given by capital omega, sigma algebra, and a risk-neutral probability measure, p tilde. Okay, under this probability space, let's define a Brownian motion given by w tilde of t. Okay, so this is a probability space. This is a Brownian motion defined on that space. And now just remember that under p tilde, w tilde basically has no drift. It basically is a martingale, so it has no drift. So now what we want to do is we want to first construct a Brownian motion with a drift. So let's do that. The Brownian motion with a drift is going to be given by w hat of t, and this is going to be equal to w tilde of t plus alpha t, where alpha is some number which we call as the drift. Okay, so the thing to notice here is under p tilde, w tilde of t has no drift. It's a martingale. And under p tilde, w tilde of t has drift alpha. Okay, so now what we want to do right now is we want to figure out what is the joint distribution of Brownian motion with a drift and its maximum. So the maximum is going to be given by m hat of capital T is equal to max of 0 is less than equal to t less than equal to capital T of w hat of t. Okay, so this basically is the maximum value that Brownian motion has taken in interval 0 to t, right? And what we want to do right now is we want to look at what is the joint density function of m hat of t and w hat of t. Okay, and remember that w hat of t basically has a drift under p tilde. So we want to look at what is the joint density under p tilde, because we want to look at what is the density of a Brownian motion with a drift, and under p tilde this Brownian motion basically has a drift. Hence we need to compute the joint density function of m and w under probability measure p tilde, okay, which is going to be given by this m w. Okay, so this is what we want to compute. Okay, just keep in mind that since our Brownian motion w hat of t at time 0 basically starts at 0, okay, m hat of capital T would be at least equal to 0, right? Because this is the max value that the Brownian motion takes between 0 and t. Since the Brownian motion starts at 0, the maximum value would be at least equal to 0. That's the first thing to notice. And since this is the maximum value, m hat of t is always going to be greater than equal to w hat of t. Okay? So graphically, if I have to denote this, if this is values of m, these are values of w, this basically would be a line which will be equal to m equals to w, and this region is the region where pairs of these two random variables m and w would take values, okay, because here m is greater than 0 and m is greater than w. So this region is where we can have pairs of these random variables taking values. Okay, so this is the region to basically consider. Okay, and what we want to do is we want to figure out what is the joint density of M with W. And under P tilde, W hat basically has a drift. So we want to look at this joint density under P tilde. Okay, and the way we're going to do it is we actually going to use Girsanov's theorem first to change this Brownian motion with a drift into a Brownian motion without drift. Okay, and let's see how that is done. For that, we basically are going to apply Girsanov's theorem. Okay, so under P tilde, this basically has a drift. Now we're going to change the measure using Girsanov's theorem such that this basically doesn't have a drift under the new measure, and let's see how we can do that using Girsanov's theorem. So first we'll just quickly recap Girsanov's theorem, then we'll apply the Girsanov's theorem to our problem at hand and see how we can make this Brownian motion basically we convert this Brownian motion to a no drift Brownian motion. Okay, so using Girsanov's theorem. Okay guys, so just a quick recap of Girsanov's theorem. So if you remember, when we were talking about Girsanov's theorem, we basically had defined a probability space, and that time we basically had defined a probability space P. So let that be the case for this discussion. And under this probability space, we said we have a Brownian motion given by Wt. Okay, and then we said let's further define an adaptive process given by theta t. Okay, then let's also define a Redon-Nikodym derivative given by z of t is equal to exponent minus integral 0 to t of theta of u dw of u minus half integral 0 to t theta square u du. Okay, and then we basically define another Brownian motion, another process given by w tilde of t is equal to Wt plus integral 0 to t theta of u du. And then we said if we define probabilities using this formula, here z basically is going to be equal to z of capital T. Okay, so z of omega dp of omega. So if we define probabilities using this formula, then the new probability measure P tilde, under that probability measure, so under P tilde, W tilde is a Brownian motion. Okay, so that's what Girsanov's theorem basically said. So we basically defined a Redon-Nikodym derivative by this formula. Then we had a process, W tilde of t defined in this way. Then we defined probabilities using this formula, and we said if we define probabilities using this formula where z is given by z of t, okay, then P tilde is a probability measure, and under that probability measure W tilde is a Brownian motion. That's what Girsanov's theorem basically said. Now we would like to apply Girsanov's theorem to the problem at hand. So we basically have, in Girsanov's theorem when we were discussing, under P, under probability measure P, we had a Brownian motion, but right now in our problem, we have a probability measure P tilde under which we have a Brownian motion. Okay, and we wanted to basically, we had a process given by W tilde. Okay, this was the formula. Now we have a process given by this. W hat is a new process. Okay, so it's in the similar form as this. And then we basically, so we can basically apply this Girsanov's theorem to our problem at hand and basically change the measure. And let's see what basically we'll get once we change the measure. Okay, so let's do that next. Okay, so first I would like to define the Redon-Nikodym derivative. So if we compare Girsanov's theorem, the process, with what we have, Brownian motion with a drift, we'll see that theta of u basically becomes, first thing we notice is theta of u is equal to, or theta of t is equal to alpha. Okay, if we compare this with this, if theta of t is equal to alpha, we'll get exactly this form. So first thing is theta of t is equal to alpha. So in this formula, we can, instead of theta of u, we can substitute alpha. And the other thing to notice is, when we were defining Girsanov's theorem, we basically were considering P under which W was the Brownian motion. But right now we basically have a situation where we have P tilde, and under P tilde we have a Brownian motion. So wherever we see W, we'll basically replace it by W tilde. Okay, so let's basically do these two substitutions. So let's define the Redon-Nikodym derivative, call it z hat of t, and use this formula right here. Minus integral 0 to t. Instead of theta of u, I'm going to put alpha. dw. Now here we had dw of u, but since we are dealing with Brownian motion under p tilde, we need to replace this by w tilde. Minus half integral 0 to t. Theta square will be alpha square du. Right? And let's solve this. We'll get, this basically would be minus alpha w tilde of t minus half alpha square t. Okay, this would be z hat of t. So what would be z? Z would be z hat of capital T. So let's replace small t by capital T. We'll get minus alpha w tilde of capital T minus half alpha square capital T. Okay, now we can do one more substitution. We know that w tilde of t is equal to w hat t minus alpha t. So let's change that. So we'll get minus alpha. Instead of w tilde of t, I'll put w hat of capital T minus alpha t. Okay, minus half alpha square t. So this becomes minus alpha w hat of t plus alpha square t minus half alpha square t. So this basically becomes minus alpha w hat of capital T plus half alpha square t. So this basically is my z hat. Okay, so all I've done is basically, Girsanov's theorem basically said this was Redon-Nikodym derivative, and in our case we basically had p tilde, so we had a w tilde instead of w. So I've replaced w with w tilde, and instead of theta of u, which was right here, we have alpha. So I've just basically done that substitution. I basically solved for z, and this is what I get. This basically becomes my Redon-Nikodym derivative. Okay, so I've defined Redon-Nikodym derivative. I have a process with a drift, which is in the same form as this. The last thing I need to do is I need to define a probability measure. So I'll define a probability measure now given by p hat of a is equal to integral a. Now here I'll have z hat, which was my Redon-Nikodym derivative, and I'm going to say z hat omega and dp tilde of omega, because now we basically want to move between p tilde and this new measure p hat. Okay, so we're going to define probabilities like this, and if you define probabilities like this, then according to Redon-Nikodym, according to Girsanov's theorem, this w hat of t therefore is a Brownian motion, no drift. Okay, so we've done the change of measure, and once we do the change of measure, this process becomes a Brownian motion, and a Brownian motion basically doesn't have any drift. Okay, so here when we were discussing Girsanov's theorem, we basically had changed the measure using this formula, and then we said w tilde was a Brownian motion. Here we have w hat. So once you change the measure using this formula right here, w hat basically becomes a Brownian motion with no drift. Okay, so now let's basically be very clear what's going on. We have two probability measures, p tilde and p hat. And I just showed you that under p tilde, W tilde of t had no drift, but W hat of t basically had a drift, right? Once we change the measure, what basically is happening to W hat of t? W hat of t, which had a drift, now basically becomes a Brownian motion with no drift. So this basically is a summary of what we've done so far. We basically applied Brownian motion as we applied Girsanov's theorem, and this process which had a drift basically became a process with no drift. Okay, and since this process has become a process with no drift, if you were to take maximum of this and this Brownian motion under this probability measure, which doesn't have a drift, the joint density is going to be given by the one that we got in the previous lecture, right? Because under this p hat, this doesn't have any drift. Hence, we can apply the same joint density formula that we learned in the previous lecture, and it was given by thing right here. So under p hat, so if you wanted to compute f hat of m t w t m w, okay, under this probability measure, if you wanted to compute this would be equal to exactly this, because under this probability measure, this Brownian motion has no drift. And when we were discussing in the previous lecture Brownian motion, this also didn't have any drift, right? So under this probability measure, this density function would be the same as this. But what we want to do is we want to figure out density under probability measure p tilde, right? Because as I said, under p tilde, the Brownian motion basically had a drift, and we wanted to figure out the joint density of a Brownian motion with a drift. So we want to figure out f tilde, not f hat. Okay? So let's basically now see how we can move between these two probability measures to figure out this function. But keep in mind, now if I had to compute expectation of a random variable under this new measure hat, e hat, is going to be given by e tilde of zx, okay? And if I wanted to compute e tilde of x, this is going to be e hat of x by z. This basically comes from a Girsanov's theorem, right? How we move between two probability measures. If you wanted to compute expectation from one to the other measure, you basically have to use a Redon-Nikodym derivative. So these two formulas basically come from our discussion on Girsanov's theorem and how we move between these two measures. So we're going to apply this now to figure out what is the joint density under p tilde. So hopefully this was clear, a little bit confusing, but hopefully the discussion actually went well. Now let's basically try to compute this, okay? And we're going to use these two equations to basically compute that. Let's see how that is done. Okay, so now what I would like to do is I would like to compute probability under the risk neutral measure that m hat of capital T is less than or equal to m and w hat capital T is less than or equal to w. Okay, and the way I can compute this is I can basically say this is equal to expectation under the risk neutral measure of an indicative function Okay, so if you remember what an indicator function was, basically it took a value 1 if this condition was satisfied, otherwise basically takes a value 0, right? So we can express probabilities as expectation of the of this indicator function, right? And these two basically are the same, but now we basically notice that we are taking expectation under the risk neutral measure. And I just showed you that if you want to basically move between these two expectations, we could basically use this formula right here. So right now we basically are computing expectation under the risk neutral measure. This can be written as expectation under the new probability measure, but then I have to divide by z. So let me first write this indicator function, m hat of t equal to m, w hat of t equal to w. But now I need to divide by the indicator by z, and my z is basically given right here. Okay, so all I'm doing is basically I'm using this formula right here. I wanted to compute expectation under the risk neutral measure of this indicator function, and I can do that under the new probability measure, but then I have to divide it by z. That's what I've done, and this basically would give me, if I take this up, I'll get e to the power of alpha w hat of t minus half alpha squared t indicator m hat of t less than equal to m, w hat of t less than equal to w. Okay, so if I compute this expectation, I'll get this probability. Now this expectation is easy to compute because if you remember, we just said that under this probability measure, w hat of t basically was a Brownian motion with no drift, right? And if this was no drift, then the joint density of this Brownian motion and its maximum was given by this formula right here. So this expectation, we can use this joint density function to compute this expectation. So let's do that. This basically expectation is then going to be given by double integral E. Now here, instead of m, I'm going to use x. Instead of w, I'm going to use y as dummy variables. Okay, so here, this would be alpha times a dummy variable y minus half alpha squared t, right? And this indicator function, if I want to compute the expectation of that, basically I can just write this whole thing here. This will be 2 times 2 x minus y by t square root of 2 pi t e to the power of minus 2x minus y whole square by 2t dx dy. And this indicator function basically is going to give us a value of 1 if x is less than, so this basically would go from minus infinity to m. The values of x would go from minus infinity to m, and y would go from minus infinity to w. Okay, this would be the integral. Now if you want to now, this basically integral is equal to the probability of, under the risk neutral measure of this, right? If you wanted to compute the probabilities of m hat t less than equal to m, w hat t less than equal to w, and if we knew what the joint density under p tilde would be, then this would be just a double integral of f of m hat of t, w hat of t, x, y, dx, dy, right? Right? If we wanted to, if we knew what the joint density function was, then we could have just straight away used double integral of this joint density function. Now, these two should be equal, okay? Hence, we can basically see that this entire integrand right here is nothing but our joint density function, right? Right, so this entire integrand basically is the joint density function, because if you wanted to compute probabilities, that's how you would compute probability, right? It would be double integral of our joint density function. So here we basically have double integral of a joint density function. So whatever is inside basically is nothing but our joint density under p tilde. So these two basically are, so from here we can write f tilde of m hat t w hat t m w is equal to, here it's 2. Now instead of x, I'm going to write 2m minus w by t, square root of 2 pi t, right? E to the power of alpha, y is w, minus half alpha squared t. Okay, so I've taken care of this term, I've taken care of this term, and I have this term, 2m minus w whole square by 2t. So this basically is my joint density of this Brownian motion at its maximum, but under p tilde, as I said, this Brownian motion basically has a drift. So this basically is the joint density of a Brownian motion with a drift and its maximum. And the joint density function is given by this form, this thing right here. Okay, it's 2 times 2m minus w t. We've taken care of this term, then we have taken care of this term right here, and this. So this basically becomes the joint density Okay, so joint density function of Brownian motion with a drift and its maximum is given by this formula right here. Hopefully, guys, that discussion was clear. So let's move on now. Okay, guys, so the last thing I would like to do today is I want to compute the density of m hat of t. Okay, and in order to compute the density of this, let's first compute, and this density I want to compute under p tilde. Okay, so in order to compute the density, first let me compute probability under the risk neutral measure that m hat t takes a value less than or equal to m. Okay, we'll compute that first, and the way we can compute that is we already know what the joint density of mt and wt is. M hat of t and w hat of t we just saw basically was this, right? So we can use the joint density function and basically integrate, and the area over which we need to integrate this, I'll just show you that area. So this basically is the value of m hat of t, this is w hat of t. Okay, this line is m hat of t is equal to w hat of t. Okay, and this we want to compute this for some value less than or equal to m. So this would be the entire area that we need to integrate the joint density over. Okay, for this area we basically have m hat of t is less than or equal to m, then m hat, so let me write this down, m hat of t is less than or equal to m hat of t greater than or equal to 0, and m hat of t greater than or equal to w hat of t, right? These three conditions are basically given by this area. So in order to compute this probability, I need to integrate the joint density function over this area. Okay, and the way I would like to basically do this integral is I want to divide the entire area into two parts. This would be my first part, this triangle, and everything under this would be my second part. Okay, so I want to compute this by integrating my joint density function, and this is the area I need to integrate this over. And what I would like to do is, this is my area number 1, this is my area number 2. So I want to integrate the joint density function over these two areas separately. Okay, so let's see how we'll do that. So if I want to integrate over this area, which is denoted by 1, this will be double integral of my joint density function. Joint density function is here. Now instead of m, I'll write x. Instead of w, I'll write y. These are my dummy variables. So let's do that. 2x minus y by t square root of 2 pi t. Okay, e to the power of alpha y minus half alpha square t minus 2x minus y whole squared by 2t dx dy. Okay, that's my first, and I want to integrate this over the first area. And if I integrate over the first area, here x would go from, this is nothing but y is equal to x. Okay, x would go from y to m, and y would go from 0 to m. So this basically would give me the integral of the density function over area 1. Okay, and then plus, I need to do another integral. I'll write down the same density function, 2x minus y by t square root of 2 pi t alpha y minus half alpha squared t minus 2x minus y whole square by 2t dx dy. But this time our x basically goes from 0 to m, and y basically goes from minus infinity to 0. Okay, so this basically would give me integral over the second part. Okay, so we can basically, so if we compute these two integrals, then we get probability that m hat is less than equal to m. So now what we need to do is we just need to compute these two integrals, and once we basically compute these two integrals, we'll get our answer. Okay, so now rest of what I'm going to talk about is just basically computation of these two integrals. Okay, hopefully you understand how we've set up the problem. We wanted to figure out probability under the risk neutral measure that m hat is less than equal to m. So we needed to integrate the joint density function over this area. Okay, and this area we've broken it down into two parts, part 1 and part 2. And I've just written down what the integral is going to be over part 1, which is right here, and over part 2, which is right here. Okay, so hopefully that was clear. Now let's just compute these two integrals, and in order to compute the integrals, let me first basically compute this inside integral. Okay, and see what we get, and then we can substitute the limits and basically solve that further. Let me just compute this integral first. So let me write down that integral. I want to compute integral of 2x minus y to square root of t square root of 2 pi t e to the power of alpha y minus half alpha squared t minus 2x minus y whole square by 2t. Okay, I want to compute this integral with respect to x. Okay, so let's compute this integral. So let's take out from this integral everything which doesn't have an x. So we basically can write t square root of 2 pi t. Okay, and here we can take out this 2 as well. And then we have e to the power of alpha y minus half alpha squared t. All of this doesn't have an x, so we can take it out of the integral, and what's left is 2x minus y, okay, e to the power of minus 2x minus y whole square 2t dx. Okay, now this integral you will see is basically equal to minus t by 2 e to the power of minus 2x minus y square by 2t. Okay, so for this integral, if we differentiate this, we'll get this. So pretty much this is the integral. Okay, so instead of this integral, I can write this and I can solve. So I'll get 2 by t square root of 2 pi t e to the power of alpha y minus half alpha square t, and I have a minus here, so I'll write minus here, and t by 2 minus 2x minus y whole square by 2t. Now this t cancels out, this 2 cancels out, so I'll basically get minus 1 by square root of 2 pi t e to the power of alpha y minus half alpha squared t minus 2x minus y whole square by 2t. Okay, so this basically is my integral with respect to x. Now basically I need to compute that when x goes from y to m. So now let's basically substitute this solution into these integrals and see what we get. So now we can write the first integral as integral 0 to m. Now instead of this integral, I'm going to just write down the result, which is minus 1 by square root of 2 pi t. Okay, and inside the integral I have e to the power of alpha y minus half alpha squared t minus 2x minus y whole square by 2t, right? And this needs to be computed from when x goes from y to m. X goes from y to m dy. Okay, and then my second integral is right here. So plus, and then I have a minus sign coming from this integral in the solution here. So I'll write minus 1 by 2 pi t integral minus infinity to 0. And again, this is the solution, e to the power of alpha y minus half alpha squared t minus 2x minus y whole square by 2t. But this time basically my x goes from 0 to m. 0 to m dy. Okay, so all I've done is basically I had computed this integral which was given inside this integral with respect to x separately, and I'm just putting the values back into this integral and evaluating these this value when x goes from y to m and when x goes from 0 to m. That's what I've done right here, and I'm going to solve this. This basically is going to be minus 1 by square root of 2 pi t integral 0 to m, and this inside thing would give me e to the power of alpha y minus half alpha squared t minus, instead of x I'm going to write m, 2m minus y whole square by 2t. Okay, minus e to the power of alpha y half alpha squared t minus, now instead of x I'm going to write y, so I'll get 2y minus y, which is y, so y square by 2t. This is dy, and then the second integral I'll write down here, 2 pi t minus infinity to 0, and the first one is it's from 0 to m, so basically I'll get alpha y minus half squared t minus 2m minus y whole square t minus e to the power of alpha y minus half alpha squared t. Now instead of, when I'm computing this, instead of x I'll put 0, so I'll get minus y squared by 2t dy. Okay, so this basically is equal to this. Now basically if you look at here, the integral goes from 0 to m, here it goes from minus infinity to 0. This integrand and this integrand is exactly the same, so we can combine these two integrals together. And this integrand and this integrand is the same, so we can combine these two integrals together. Okay, so let's see what we're going to get. We'll get minus 1 by square root of 2 pi t. If we combine these two integrals together, this integral was going from 0 to m, this is going from minus infinity to 0. So if we combine them, we'll get integral from minus infinity to m. Okay, this is the integrand is the same, so let me write it down here. Alpha y minus half alpha squared t minus 2m minus y whole square by 2t, right? dy. That's my, if I combine these two integrals, that's what I'm going to get. Then let me combine these two integrals. So I have a minus sign here, I have a minus sign here. So minus minus would become plus by square root of 2 pi t integral minus infinity to m. Okay, here again integral was going from 0 to m and minus infinity to 0. If you combine the two, integral would go from minus infinity to m, and let me write down this integrand, e to the power alpha y minus half alpha squared t minus y squared by 2t dy. Okay, so what we need to do now is we need to basically compute these two integrals, and basically we'll get the answer. And in order to compute these integrals, let us just first simplify what's there in the exponent. Okay, for the first integral, I'm going to do a side step here. First integral, let's write down what the exponent value is. It's alpha y minus half alpha squared t minus 2m minus y whole squared by 2t. This can be written as 2t 2 alpha yt minus alpha square t square 2m minus y whole square. Okay, now I would like to see what basically y minus 2m minus alpha t whole square is. Okay, so I want to see what this basically expands to. This will expand to y minus 2m square plus alpha square t square minus 2 y minus 2m alpha t, right? So now I can multiply both sides with a minus sign, so I'll get minus y minus 2m, okay, minus alpha t whole square is equal to, now instead of y minus 2m, I want to write this as 2m minus y whole square. And I can do that because I have a square here, so it doesn't really matter. Okay, I can rewrite this like this. And I'm multiplying everything by minus, so I have a minus here. I'll have a minus alpha square t square. And let's open the brackets here. I'll have a plus 4 alpha, plus 2y alpha t. And this was going to be plus and minus 4m alpha t. Okay, so here I had 2m minus y square minus 2m minus y square minus alpha square t square plus 2 alpha yt. This part is the same as what I have here, so I can bring this term on the right hand side, so I'll get minus y minus 2m alpha t whole square plus 4m alpha t is equal to this part. Okay, so instead of this part I can write this, right? And I can substitute that here. That's my first thing that I've done. Let me also solve what we have in the exponent right here. In the exponent right here we have alpha y minus half alpha square t minus y square by 2t. This is nothing but 2t alpha y minus alpha square t square minus y square. Okay, and this can be written as, this is nothing but y minus alpha t whole square by 2t. Okay, so this simplifies to this, and this simplifies to this. So let me substitute these two values in these integrals and basically solve. Okay, so I can put this value right here, this value right here, and this value right here. Okay, so and let's basically now go back to our integral. So I'll get integral was minus 1 by square root of 2 pi t, and integral was going from minus infinity to m. Now e to the power, instead of this I can write this divided by 2t. So I'll write minus y minus 2m minus alpha t whole square plus 4m alpha t whole divided by 2t dy, and my second integral is going to simplify to plus 1 by square root of 2 pi t integral minus infinity to m. Instead of this I'm going to write this, e to the power of y minus alpha t whole square by 2t dy. Sorry, one small mistake I've made. This basically is minus of this, okay, because we have a minus y squared. So when we expand this, we need to put a minus sign here. So we have a minus here, okay. So now we need to basically solve these two integrals, and we're going to do that by change of variable, okay. So the first integral, this part doesn't have a y, so I can take this part out. So this integral can further be simplified too. We have a 2, this will be minus 1 by square root of 2 pi t. And when I take this, this will be dt, you will get 2mx e to the power of 2m alpha. Okay, so I've taken this term out, and basically I'm left with minus infinity to m e to the power of y minus 2m minus alpha t whole square by 2t dy, and the second integral would be plus 1 by square root of 2 pi t integral minus infinity to m e to the power of minus y minus alpha t whole square by 2t dy. Okay, so in order to solve the first integral, what I can do is I can say y minus 2m minus alpha t by square root of t is equal to z. If I do this substitution, then basically y would become alpha square root of t times z plus 2m plus alpha t. So dy then basically becomes square root of t dz. Okay, and here what I'll do is I want to do y minus alpha t by square root of t as z. Then y basically becomes square root of t times z plus alpha t. Dy then becomes square root of t dz. Okay, so let me rewrite this integral with this change of variable. So this would become minus e to the power of 2m alpha by square root of 2 pi t. Now this integral was going from minus infinity to m. Now if instead of y I put minus infinity here, z would also go from minus infinity, and if I put instead of y I put m here, I'll get minus m minus alpha t, minus m minus alpha t by square root of t. Okay, and here I'll get e to the power of minus 1 by 2. This entire thing basically was z, so this becomes z square square root of t, and dy was square root of t dz. Okay, so square root of t and this cancels out, and okay, so this basically is my first integral, and my second integral basically is plus 1 by square root of 2 pi t. And here, if y is minus infinity, z would be minus infinity. If y is m, z would be minus alpha t by square root of t. And again inside I'll get minus half z square, and dy was square root of t dz. Square root of t, this cancels out, so basically I'm left with minus e to the power of 2m alpha by square root of 2 pi e to the power of, integral from minus infinity to minus m minus alpha t by square root of t minus half z square dz plus 1 by square root of 2 pi minus infinity to m minus alpha t by square root of t e to the power of minus half z square dz. Okay, now this 1 by square root of 2 pi and the integral of this is nothing but cumulative standard normal distribution. So this can be written as e to the power of minus e to the power of 2m alpha, and this would basically give me the cumulative standard normal minus m minus alpha t by square root of t. Okay, and same thing here. This entire thing is basically cumulative standard normal distribution, and because we basically are going from minus infinity to this would just be n of minus alpha t by square root of t. Okay, this would be my probability that this basically we were calculating probability under the risk neutral measure that m hat of t is then equal to m. So I'll get this formula for my cumulative probability distribution. Okay, my cumulative probability distribution of m of t is given by this particular formula. And now if I wanted to basically figure out what is the PDF, what is the density function, I just need to differentiate this with respect to m. Okay, if I differentiate with respect to m, I'll basically get my density function. So let's differentiate this and basically get the density function next. Okay, so let's basically differentiate this. I want to take differential with respect to m of my probabilities that m hat of t is less than or equal to m. So I want to differentiate this with respect to m. So let's do that. For the first time, we'll apply the chain rule. This would be given by, I have minus e to the power of 2 m alpha. Then differentiating this, I'll get 2 alpha, okay, times n to the power of n of minus m minus alpha t by square root of t. Okay, that's my first term. Then I'm gonna get, minus e to the power of 2m alpha, and this would give me n dash of minus m minus alpha t by square root of t. And I need to differentiate this. I'll get a minus 1. Minus minus will become plus. Okay, that takes care of my first term, and then this one would be n dash of m minus alpha t by square root of t. Sorry, this would be when I differentiate the inside, I'll get minus 1 by square root of t. So I have forgotten a square root of t here. And similarly, this would become n dash of this, and I have to differentiate this part with respect to m, and I'll get 1 by square root of t. Okay, and this I can rewrite as minus 2 alpha e to the power of 2 m alpha n of minus m minus alpha t by square root of t, and here I'll get plus e to the power of 2 m alpha by square root of t, and n dash would basically give me 1 by square root of 2 pi e to the power of minus m minus alpha t by square root of t whole square, plus this would be 1 by square root of t, 1 by square root of 2 pi e to the power minus half m minus alpha t by square root of t whole square. Okay, so that's pretty much what we're going to get. We can now simplify this a little bit further, do a little bit of algebra and simplify it together, but I'm not going to do that. But basically this was the idea. We basically had a probability of we had a cumulative distribution function, and we need to differentiate this with respect to m, and if we do that, we'll basically get the density function. So I've differentiated this. Now if you want, you can simplify this further by doing a little bit of algebraic manipulation, but I'll leave the discussion right here. Okay, so this basically is the density function of m hat of t under p tilde. Okay, so hopefully guys this was clear. We basically talked about in this lecture, we basically talked about the joint density of m hat of t and w hat of t under risk neutral probability measure. Then we looked at the cumulative distribution function of m hat of t under p tilde. And after differentiating this with respect to m, we basically got the density function for m tilde of t under our risk neutral measure, right? So hopefully that discussion was clear. Now these results, we'll actually use them when we are looking at these exotic options. Okay, so whatever we learned in the previous lecture, what we've learned in this lecture will be used from next lecture onwards. Okay, so I'll see you guys then.